Welcome you all in the lecture number 9 of Abstract Algebra MTL 6051. In this lecture, we will going to discuss some important examples of factor group and one of the most important theorem that if G is any group and G by ZG is cyclic, then G is abelian. And using this theorem, we will see some important example, right? Let us see one of the important example of it. This example we already discussed in previous lecture. Now let us see what more information we can draw from here. If G is equal to Z4 cross Z2, right? It is a group and H is subgroup generated by 2, 1. 2, 1 is the element of 2, 1 belongs to Z4 cross Z2. Then what is the structure of this factor group? That Z4, Z2 and Z4, Z2 by H. That is Z4, Z2 and what is H? H is generated by 2, 1. Right? What is the structure of this? We have to find out the structure of this. Now see, what is the element of Z4 cross Z2? Z4 cross Z2 means 0, 1, 2, 3 cross 0, 1. Right? Then order of this Z4 cross Z2 is 8. See, what are the element of this Z4 cross Z2? 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, 2, 1, 3, 0 and 3, 1. Right? This thing. Total 8 element. Now see, what is H? H is generated by 2, 1. Then consider 2, 1. Now operate this 2, 1 with 2, 1. Right? What is this? 2 plus 2 is 4 and 1 plus 1 is 2. What is this 4? 4 is element of Z4. What is this 2? 2 is element of Z2. Right? This 4 is equivalent to 0 in Z4 and 2 is equivalent to 0 in Z2. Right? Then this 2, 1 plus 2, 1 is equal to 0. It means order of this element is 2. Right? That is H is 0, 0 plus 0, 0 and 2, 1. Right? Then what is the order of this factor group? Since we know that order of G by H is equal to order of G divided by order of H. Right? Then what is order of G? Order of Z4 cross Z2. And what is order of H? This is 8 and this is 2. Then this quotient group Z4 cross Z2 by H, it containing 4 elements, right? An element of the type AB plus H, such that A belongs to Z4 and B belongs to Z2, right? This thing. What is H? H is this, right? Now see, what is AB? This AB, this ordered pair AB belongs to Z4 cross Z2, right? Then what is the element of Z4 cross Z2? 0, 0, 0, 1, dots 1 up to 3, 1. Now 0, 0 plus 0, 0 plus H. What is 0, 0 plus H? H means this na? 0 0 plus h is 0 0 and 2 1. Okay. 0 1 plus 2 1. What is 0 1 plus 2 1? That is 0 1 plus 0 0 and 2 1, right? Then 0 1 plus 0 0, that is 0 1, comma 0 plus 2 is 2, 1 plus 1 is 2, that is 0. This 0 plus 2 is 2 and 1 plus 1 is 2 and 2 in Z2 is equal to 0. Okay. Similarly, we can find the other element, right? Next, this one is 2 plus 2, right? This thing is this one, 2 0 plus 2 1. This is equal to 2 0 plus 0 0 comma 2 1. 2 0 0 0 is equal to 2 0 and 2 0 plus 2 1 is equal to 2 plus 2 is 4, 4 is equal to 0 and 0 plus 1 is 1. So therefore this is 1, not 0. Okay. Okay, these are the elements. Now see, now Z4 cross Z2, right, by H is equal to these four elements, 0 0 plus H, 0 1 plus H, right? Remember that H is this 2 1. 0 0 plus H, 0 1 plus H, 1 0 plus H, 1 1 plus H. Okay. Then order of this Z4 cross Z2 by H is 4, right? Order of this is only 4 element, right? Then every group of order 4, this is group, this is factor group, and order of this is 4. This is either isomorphic to Z4 or Z2 cross Z2. Okay. Now see, one element 1 0 plus H in Z4 cross Z2 by H is isomorphic to sorry, one element 1 0 plus H belong to this is sorry, not isomorphic, sorry, this is generator, this is generator of Z4 cross Z2 by H. Okay, this is generator of H. If this is generator of H, then Z4 cross Z2 by H, then Z4 cross Z2 by H is cyclic. This Z4 cross Z2 by H is cyclic. Then this is abelian also. Every cyclic group is abelian. This is abelian. Then this Z4 cross Z2 by H is isomorphic to Z4. Okay. Now see another example. If G is equal to Z2 cross Z8 and H is 1 1, then what is the structure of Z2 cross Z8 by H? That is Z2 cross Z8 and subgroup generated by 1 1. Okay. Then we have to find out Z2 cross Z8 by H. Now, what is order of H? Order of H that we can define as LCM of, see this, LCM of order of 1 in Z2, comma, and order of 1 in Z8. Okay. Then LCM of what is order of 1 in Z2? 2. What is order of 1 in Z8? 8. This LCM is 8. Okay. Then this order of this H is 8. Right. Then order of Z2 cross Z8 by H is equal to order of this Z2 cross Z8 is 16 and order of H is 8, and this is equal to 2. Okay. Then this group, this factor group Z2 cross Z8 by H is isomorphic to Z2. Okay. Now let us see one another example. If K divides N, what is K? K is any positive number, positive integer, not number, any integer, right? And K divides N, right? Then we define UKN. UKN is normal subgroup of UN. This UKN is normal subgroup of UN. What is UKN? Basically, UKN is all the numbers x from UN, means x from UN, such that if we divide x by k, then our remainder is 1. It means x congruent to 1 modulo k. All such numbers x in UN is element of UKN. Then this UKN is, if we define UKN in this way, then this UKN is normal subgroup of UN. This we have to show that, right? Let us see. Before proving the UKN is normal subgroup of UN, we have to show that UKN is subgroup of UN. Okay, let us see. Let for subgroup, we know that if G be a group and H is subgroup for this, if AB belongs to AB belongs to H, then AB inverse belongs to H, right? If this property hold, then H is subgroup of G. This theorem we already proved in previous lecture. Now see, let AB belongs to UKN. Then by definition, A congruent to 1 modulo K and B congruent to 1 modulo K, right? By definition of congruent, 1 congruent to B inverse modulo K, right? Or B inverse congruent to 1 modulo K. Then using these two, AB inverse modulo K, right? AB inverse congruent to 1 modulo K. See, how AB inverse congruent to 1 modulo K? This thing, A modulo K, B inverse modulo K, whole modulo K. This is equivalent to 1. It means AB inverse congruent to 1 modulo K, right? This means if we divide AB inverse by K, then our remainder is 1. It means AB inverse belongs to UKN. Hence, UKN is subgroup of UN. Okay, what is UN? UN is abelian group, right? And subgroup of abelian group is normal, right? UKN is subgroup of UN, but UN is abelian group, right? Every subgroup of abelian group is normal. Therefore, UKN is normal subgroup. UKN is normal subgroup of UN. Okay. Now construct U321. First we will know what is U21. U21 containing all those numbers which are relatively prime with 21. 1 is relatively prime with 21. 2 is relatively prime with 21. 4, 5, 8, 10, 11, 13, 16, 17, 19 and 20. This is U21. Now U321 means how many element in U21 that if we divide by 3 and which gives us remainder 1. What is those numbers? 1. 4 if we divide by 3, remainder is 1. Right? 5 if divide by 3, then remainder is 2, then 5 is not here. 8 if we divide by 3, then remainder is 2. 10 if we divide by 3, remainder is 1. Okay. 11, no. 13, yes, remainder is 1. 16, 16 is also here. 17, no. 3 5 15, 17, that remainder is 2. 19. Okay. These are the element of U321. Okay. What is order of U321? 6. U321. This order is 6. Okay. Every group of order 6 is either isomorphic to Z6 or S3. This U321 is isomorphic to Z6. Why? Since this is abelian. This is abelian. S3 is not abelian. Therefore, this U321 is isomorphic to Z6, not S3. Now see, this is one of the most important theorem and we will solve a lot of problem using this theorem. If G be a group and Gy is Zg, first see whether Gy Zg is exist. What is Gy Zg? Right? It is factor group. Right? For any factor group G by H, we know that H is normal subgroup of G. Then what is G by Zg? Zg is subgroup that we already proved is subgroup of G. Right? Then Zg is normal subgroup since Zg is abelian. Okay? Normal subgroup of G. Therefore, G by Zg exists. G by Zg exists. Okay, no problem. This G by Zg exists. Let us see the statement of the theorem. Statement of the theorem says that if G be a group and G by Zg is cyclic, remember that this is cyclic, then G must be abelian. Right? Then G is abelian. Now see the proof. What is G? G be a group. What is Zg? Zg is center of G. Okay. What is the element of G by H? Factor group. Element of this quotient group is AH, where A belongs to G. Okay. Then element of G by Zg is AZG. Right? For H, replace H by Zg. Element of this is AZG. A belongs to G. Okay. What is G by Zg? Cyclic. What do you mean by cyclic? There exists one element in G by Zg, which is the generator of G by Zg. Okay. Let us consider one element. X Zg in G by Zg such that G by Zg is equal to X Zg. It means X Zg is generator of G by ZG, right? Why? Since this is cyclic, it is given this is cyclic, then there exists at least one element which is generator of this group. Okay. Now see, AZG and BZG, right, belongs to G by ZG. Then AZG and BZG be any two element of G by ZG, and since XZG is generator, XZG is generator, then this XZG generates AZG and BZG. Okay. Then there exists, if this generate A into ZG and B into ZG, then there exists N and M such that, what is NM? NM are positive integer, right? This belong to, capital N. This belong to capital N. Then this AZG is equal to EXN ZG. See here, we know that AH and AH, this is equal to A to H, right? Since what is the operation? AH BH is equal to ABH. Similarly, AH is equal to A into AH, that is A square H. Okay. Then AZG is equal to XNZG. AZG is equal to XNZG, and BZG is equal to XMZG. Okay. Now A can be written as A dot E, right? A is A dot E, and this belong to AZG. A is A and E belong to ZG. Okay, no problem. Then this is equal to, what is A? A is X and ZG, right? It means A belongs to X and ZG. This means A is Xn into one element of ZG. Say this is Z1. Say this is Z1. Similarly, B is Xm into one element of ZG, that is Z2. Say, right? Xm Z2. Now XY. What is XY? XY is AN Z1, and what is Y? AM Y2. Okay. Then this can be written as this AM, right? What is Z1? Sorry, this is Z2. Z2. Okay. Wait 1 minute. This XY is equal to AN Z1 and Y is AM Z2. Okay. Then this AN Z1 AM Z2, right? What is this? AN AM Z1 Z2. Why? Since what is Z1? Z1 belongs to ZG. Then this Z1 commute with every element of the group. What is AM? AM is element of group. What is Z1? Z1 is element of ZG. Therefore, this Z1 AM is equal to AM Z1. Okay? And this one, right? Similarly, AN AM is equal to AM AN, and AM AN Z2 Z1. This thing we can write it AM Z2 and Z1. Why? Since Z2 belong to ZG, therefore this commute with, right, every element of ZG. Then every element of G. Then this is equal to AM Z2, this is Y, and AN Z1, this is X. Right? Then XY is equal to YX. Hence, this is true for all AXY in G. Hence, G is abelian. Okay? It means that if G by ZG is cyclic, then G is abelian. Okay? Now, converse of above theorem is also true. It means if G is abelian, what is the converse? If G is abelian, then G by ZG is cyclic. Okay? If G is abelian, then G by ZG is cyclic. Now let us see some example based on above theorem. If G is Q4, if G is quaternion group, then what is the structure of Q4 by Z Q4? Q4 by Z Q4. We know that Q4 is plus minus 1 plus minus I plus minus J plus minus K. Okay? And what is ZQ4? That is 1 and minus 1. Okay. Then what is Q4 by ZQ4? Q4 by ZQ4 is, what is the order of Q4? 8. What is order of ZQ4? 2. Right? Then what is order of Q4 by ZQ4? This is 8 by 2. This is equal to 4. Then this Q4 by ZQ4 is either isomorphic to Z4 or isomorphic to Z2 cross Z2. Right? Now, if this Q4 by ZQ4, right, is isomorphic to Z4, then what happens? What is Z4? Z4 is cyclic, right? This Z4 is cyclic. Please wait 1 minute. If Q4 by ZQ4 is isomorphic to Z4, then this is cyclic. This Z4 is cyclic. So this is also cyclic. Right? If this is cyclic, then what is Q4? By above theorem, then Q4 is abelian. Okay? Means G by ZG is cyclic, then G is abelian by above theorem. The Q4 by ZQ4 is isomorphic to Z4. Z4 is cyclic, therefore abelian also. Then this is also abelian, Q4 by ZQ4. Right? And this is cyclic. And this is, if this is cyclic, then what is Q4 by this theorem? This theorem, right, says that Q4 is abelian. But we know that Q4 is not abelian. Q4 is, if this is isomorphic to Z4, then Q4 is abelian. But we know that Q4 is not abelian. Right? Then Q4 by ZQ4 is isomorphic to Z2 cross Z2. Now see, if G is D6, right, dihedral group 6, then what is D6 by ZD6 structure of this quotient group? D6 by ZD6, right? D6 containing how many elements? 12. What is the order of this? D6 containing 12 elements, 2 into n, that is 2 into 6 is 12. What is Z D6? It containing 2 elements. Okay. Then what is this? 6. It means D6 Z D6. Right? Order of this is 6. Then this is isomorphic to either Z6 or ES3. It containing also 6 element and ES3 has 6 element. Then this is isomorphic to this one or this one. Suppose if D6 Z D6 is isomorphic to Z6, then this Z6 is cyclic, right? Therefore, this D6 by Z D6 is cyclic. Okay, this is cyclic means D6 is abelian by above theorem, but this is not true. If this is not true, then D6 by Z D6 is isomorphic to ES3. It means what is the structure of this? The structure of this is similar to the S3, right? Identity 1 2 1 3 2 3 1 2 3 1 3 2, right? One element of order 1, these are order 2, and these are order 3. See, this is the structure of D6 by ZD6. Okay. Okay. If order of G is PQ, it is given. What is order of G? It is P into Q. What is PQ? PQ are prime number. Then P and P is less than Q, and G is non-abelian. Right? Following things are given. Order of G is PQ, P is less than Q, and G is non-abelian. Non-abelian. Then order of ZG in this case is 1. Okay. Let us see. What is order of G? This is PQ, where P is less than Q. Okay. What is ZG? ZG is subgroup of G. We know that. Then by Lagrange's theorem, order of ZG divides order of G. This thing. Then order of ZG divides PQ. Okay. If order of ZG divides PQ, then following things happen. What is order of ZG? Either 1 or P or Q or PQ. Because if order of ZG divides 6, suppose, then what is 6? 6 is 2 into 3. Then what is order of ZG? This is either 1. What is the divisor of 6? 1, 2, 3 or 6. It means 1, P, Q or PQ. Okay. Now suppose, right? Let us consider case first. If order of ZG is PQ, suppose this case, right? What is order of ZG? Order of ZG is either 1 or P or Q or PQ. Let us consider case first. If order of ZG is PQ, then what is the order of G by ZG? This is order of G by order of ZG, right? That is 1. PQ by PQ, that is 1. Then G by ZG is isomorphic to Z1. What is Z1? This is abelian, right? Or cyclic. Then what is this? This implies that G is abelian. But this is contradiction since G is not abelian. Okay. Then order of ZG cannot be PQ. Means first case not possible. Now come to the second case. Case 2, if order of ZG is Q, if order of Zg is Q. Then what is order of G by Zg? Order of G by Zg is order of G by order of Zg. What is order of G? PQ. What is order of Zg? Q. Then this is P. Then order of G by Zg is P. Okay. Then G by Zg is isomorphic to Zp. What is Zp? This is cyclic. Every group Zp where P is prime number, this type of group is always cyclic group. Okay. This is cyclic. This is isomorphic to Zp. Therefore, this also cyclic. Cyclic, then what is G? G is abelian, right? But this is not possible since it is given that G is non-abelian. G by Zg is isomorphic to Zp implies that G is abelian by the above theorem. But G is not abelian, so this is not possible. Similar case to second one. Order of Zg is also not possible to P, right? Then order of Zg is not equal to P, Q or PQ, right? Then what is the remaining thing for order of Zg? Order of Zg must be equal to 1. Okay, this is the complete proof of this problem. Now see, order of G is 55. Let us see one example. Order of G is 55. What is 55? 5 into 11. Okay, 5 is less than 11. Then what is Zg? Right? Zg, if G is non-abelian, see what is G? Suppose G is non-abelian, then above problem says that Zg is isomorphic to Z1. Why? Since order of Zg is 1, then this is isomorphic to Z1. But if G is abelian, if G is not abelian, then Zg is isomorphic to Z1. Okay. But if G is abelian, then G is isomorphic to Z55. Implies that G is abelian, then G is equal to Zg. No doubt. Then Zg is isomorphic to Z55. Okay. Okay. Now we will stop here. In next lecture, we will discuss some more important examples. Okay. Thank you.